It's one small step for man, one giant leap for mankind.
A sleek jet aircraft soars through a clear blue sky. A hard-working piece of agricultural machinery plies an ocean of fertile farmland. An airplane, a farm implement. As different as each of them is from the other, they share a most important feature in common. Each is made by a company that is committed to the commercial use of space. But along with that similarity, there is a contrast as well. The airplane maker is conducting microgravity research in an area that is totally new to it, pharmaceuticals. On the other hand, the agricultural equipment company will be using what it learns from microgravity research to improve a basic bread and butter manufacturing process it has used for years, producing cast iron components for its farm machinery. There's something else worth noting about these two companies. Agricultural products are America's leading export. Airplanes are second. The airplane maker and the farm equipment manufacturer are just two examples of a small band of forward-looking, forward-thinking, and forward-doing companies that are committed to improving their competitive positions and their profit pictures through the commercial use of space. They are companies working in everything from electronic crystals to internal combustion engines. They are companies that already have taken the first steps toward profiting from the commercial use of space. But most companies are not yet involved in commercial activities in space. Many are uncertain as to just what space commercialization means. To assist individual managers in private companies to remove that uncertainty, as well as to support America's national space commercialization goals, Lewis Research Center has formed an Office of Space Commercialization. The purpose of that office is to help a company uncover and assess the relevance of commercial space activities to its operations. Manager Harvey Schwartz explains.
The general field of commercial space activities can be broken down into four major areas. First, space is a vantage point from which we can communicate, forecast the weather, and from which we can also observe and map the Earth's resources. Secondly, space is a location to which the private sector can provide transportation services. Third, space is also a location where we require other kinds of services, such as satellite repair, which are now done by the federal government. And fourth, space is a unique environment in which we can conduct microgravity research on new processes and products. The Office of Space Commercialization here at the NASA Lewis Research Center can act in a sense as a broker between the needs of the private sector and the engineering and research capabilities we have here in great depth.
Lewis can offer researchers hands-on help in a host of scientific and engineering disciplines: communications, space power, launch vehicles, microgravity sciences, metals and alloys, composites, ceramics and glasses, electronic materials, fluid physics, and combustion. The assistance that Lewis can give might range from simply answering general questions to offering expert and experienced counsel to help answer the one all-important specific question: can I improve my company's operations by examining the physical principles on which they are based in a microgravity environment? For a company to pursue a commercial venture in space, the project must be broken down from conception through execution into a series of steps, each of which must fit the duration and resource requirements of that company's planning horizons. That makes it possible to review progress periodically and reassess the commercial potential of a project before committing more time and money to it. It's a sensible step-by-step approach that Lewis can support with unique, tailor-made facilities, particularly in the area of microgravity research. The first of these facilities is the Microgravity Materials Science Laboratory. The purpose of the MMSL is to give American companies a competitive edge in their markets by helping them take the first step toward developing better products and processes through microgravity research. Specifically, the MMSL offers a low-cost, low-risk way for researchers to test new ideas for materials science and process research before starting formal efforts in their own laboratories. Thomas K. Glasgow, manager of the MMSL at Lewis, elaborates.
A company should consider the use of the microgravity environment if it is interested in growing more perfect semiconductors or optoelectronic crystals. The microgravity environment is also a good laboratory for studying what are usually convection-dominated processes, such as combustion. Another reason for looking at the microgravity or space flight environment is for preparation of corrosive glasses, such as those which might interact highly with a container on Earth. For these processes, or any other process which would be dominated by convection or gravity effects on Earth, the microgravity environment of space offers an appropriate laboratory.
The MMSL has equipment with functional capabilities similar to space shuttle flight hardware. Major items in the MMSL are a general-purpose furnace, which simulates one of the 3 furnace cavities flown aboard the shuttle, an electromagnetic levitating furnace with a 1-second instrumented drop tube for containerless solidification. Up to 10 samples a day can be dropped. An isothermal dendrite growth apparatus to observe the growth and shape of individual free dendrites in a transparent supercooled melt. A general-purpose resistance-heated high vacuum furnace to heat-treat samples in a vacuum or an inert gas atmosphere. A single-axis acoustic levitator to study the containerless solidification of reactive and unusual glasses. A high-temperature batch melt furnace for glasses. And a hot stage microscope to observe phase separation in glasses. In addition, a visiting researcher will be supported by Lewis's computer capability and by the center's microstructural characterization, chemical characterization, and spectrometric analysis facilities. The Microgravity Materials Science Laboratory, however, is only the first step that can be taken by a researcher at Lewis. A typical project might begin by establishing 1G baseline data in the MMSL and then proceeding, if indicated, to a drop tower or to a research aircraft to qualify the project for spaceflight. Lewis has 2 drop towers. The larger of the two is designed to provide reduced gravity exposure for either 5 or 10-second periods. Experiment packages fall through a distance of 430 feet during a 5-second drop. For a 10-second simulation, the experiment package is propelled by means of a pneumatic accelerator from the bottom of the tower to within inches of the top before falling back. Reducing the air pressure inside the shaft makes possible an experimental drop in which gravitational force has been reduced to 1/100,000th of its normal Earth value. High-speed motion picture cameras inside the experiment vehicle record the experiment during the period of reduced gravity. Statistical data such as pressure, temperature, and acceleration are recorded by onboard instrumentation and transmitted to the control room. A clean room is available for the preparation of experiments that are particularly sensitive to contamination, even from normal atmospheric conditions. An example would be certain fluid physics studies. During testing, all activity in the experiment chamber is monitored on closed-circuit television in the control room. A cross-sectional scale model of the test chamber provides a simple visual explanation of the system and its capabilities. Most of the facility is below ground level. Inside the concrete shaft is a 20-foot diameter steel vacuum chamber. In the model, a vehicle containing an experiment is shown at the top of the chamber, ready for a 5-second drop. At the end of a drop, the experiment package is brought to a stop in a container of polystyrene pellets. The experiment stops in approximately 15 feet and experiences a force of about 35 Gs. The package is designed so that there is no damage to the experiment or to the recording equipment during deceleration. Another frequently used Lewis facility is a smaller 95-foot drop tower which can provide 2.2 seconds of reduced gravity. The small drop tower is open to the atmosphere. Reduced gravity conditions are achieved by enclosing the experiment package in a shield to isolate it from aerodynamic drag. Longer periods of reduced gravity are possible with research aircraft. Lewis has a Learjet Model 25, a small passenger jet with a modified interior that serves as an airborne reduced gravity laboratory. By flying parabolic trajectories, it can produce variable low gravity conditions for as long as 20 seconds. In 1969, when Neil Armstrong stepped onto the moon, mankind took its first giant leap in space. Today, commercial potential offers us the chance to take the second. Commercial use of space is a tremendous opportunity for the researcher with good ideas and for the manager who wants his company to be in a unique market position in the years ahead. But it is an opportunity that can be lost by a wait-and-see attitude. The decision to go forward is being made by those managers who are focusing on what is possible and are willing to explore new approaches to meeting the competitive and technical challenges that lie before them. To take the first step requires courage. However, the opportunity to discover something totally new through microgravity research occurs only once in all of human history. That time is right now.